Okay, so today we're going to look at independent events. So yesterday we looked at problems where knowing one event occurred changed the probability of the other event occurring. That would be conditional. But now we're going to go the opposite way. It's also possible that knowing one event occurred does not change the probability of the second event. In this case, the events are called independent. Suppose I flip a coin twice. Does knowing the outcome of the first flip change the probability of the second flip? No. They are independent of each other. Suppose I survey all the students and note their gender and handedness. The totals are shown in the table below. If the variables were independent, what values would I expect to find in the table above? Let's pretend the probability that a person's right-handed is 90%. So gender and handedness have nothing to do with one another. So if it's a 90% probability that they're right-handed, I should have 63 males that are right-handed and 72 females that are right-handed. Again, because it shouldn't matter. So two events, E and F, are independent if and only if the probability of E, given that F already happened, should equal the probability of E in the first place. So it shouldn't even matter. So the conditional shouldn't matter. In other words, knowing that F occurred doesn't change the probability of E occurring. The concept of independence will be very important in mostly second semester. If the events E and F are independent and the data we have is from a random sample, then we can do an approximation. In other words, the probabilities may not exactly be the same because of sampling variability. How close they need to be, we'll get there in chapter 12. So two events are dependent if they're not independent. So there's two tests for independence. These are the two you're going to need to know. They're not on your formula sheet. The first one is the one that I wrote above. It sort of makes sense to me. E, given that F already happened, should just equal E. This is the one that AP readers tend to like when students use. I'm going to show you both in the examples that we're going to do today. On your quiz or your test, you can just pick one. So again, these are not on your formula sheet. That's why I think this one makes more sense. The second one for independence is the probability of E and F happening should equal the probability of E times the probability of F. So you need to know both, but like I said, you can always pick just one to do on the test or the quiz. So we're gender and survival independent on the Titanic. So what we're going to do, I'm going to look at gender and survival. I'm going to look at male and survived. And I'm going to do both of these. So I'm going to do this one first. So I'm going to look, does the probability that they're male, given that they survived, equal to the probability that I had a male person on the Titanic in general? Then I'm going to do it the second way, just so you can see both. We're going to look at the probability that they were male and they survived should equal the probability of male times the probability that they survived. So I'm going to show you both, but again, you can just pick one. So if I go back to my notes from 6-4, male survived. There were 711 people that survived. Of those that were male, that's 367. How many males total? There was 1,731 males total out of 2,201. So here's where you want to use decimals. They should be exactly the same unless you're looking at a sample, which here we are not. So this is 0.516, 0.786, so these should be not independent. Now, when I do the second one, I'm going to get different decimals, but they should still give me the same conclusion. So male and survived, there was 367 males that survived out of 2,201. Again, there were 1,731, and there were 711 survivors. So this one takes a little bit more calculator work. But sometimes it depends on the problems ahead of time, which we'll see in a second. So this is 0.167. And then all I'm going to do for the second part, I'm going to use my parentheses. So 1731, 2201, 711, 2201. If you can see that. So 0.254. So again, not equal, so not independent. So when you're doing this on a quiz or test, there's a couple things you need to keep in mind. First of all, I cannot read your mind. Do not give me E and F. I'm not going to know what E is. I'm not going to know what F is. Unless you want to give me a key off to the side. Use the words in the problem. Even just like here I have M and S, I could pretty much figure out that's male survived. You have to show work. You can't just say this is not equal to that, not independent. You need to show me calculations. Do not try and write it out in words. Show me the calculations. Okay, so let's try another example. Now this is an oldie but a goodie, and I will say Mr. Ginter wrote this. 42% of people from Ohio are illiterate. 5% of people from Ohio have attended, at some point, The Ohio State University. Assume the two groups are independent. So instead of trying to prove things are independent, I can tell you things are independent, and then you can use the independent rules. So let's find the probability that I pick an Ohioan that's illiterate and has gone to The Ohio State University. So here's where knowing the second one comes in handy. This is because they're independent. This is just the probability that the person's illiterate times the probability they went to OSU because of the independent rules. So I'm going to take 0.42, I'm going to multiply by 0.05. So 0.021. Find the probability an Ohioan is illiterate or has attended The Ohio State University. So the probability that they're illiterate or they went to OSU. So if I use my rules, that's the probability that they're illiterate plus the probability they went to OSU. There's obviously some overlap, so minus the overlap. Oops, that should be OSU. So I'm going to do illiterate plus OSU minus what we just picked. So 0.42 plus 0.05 minus 0.021. So 0.449. Find the probability an Ohioan is illiterate given that they've gone to the Ohio State University. So again, now we're going to do a conditional so that they're illiterate given they went to OSU. But again, so if I use the formula, this would be the probability that they're illiterate and they went to OSU over the probability that they went to OSU. So illiterate and they went to OSU was 0.021 from part A. OSU is 0.05. When I divide, I get 0.42. 42%. Again, this is equal to the probability that they're illiterate since they are independent. So I didn't necessarily have to do all of this work. I could just say they're equal. It's equal to 42% since they're independent. Now, if you do all this work on a quiz or a test, am I going to mark it down? No. But it just shows you kind of how the fractions work. Okay, during the Civil War, carbolic acid was often used on patients during amputations. If carbolic acid was used, 34 out of the 40 patients lived. If it was not used, 19 out of 35 patients lived. Find the probability that carbolic acid was used and the patient died. So I'm going to make myself a two-way table. Usually when I have some sort of data in terms of frequency, I'll make a table. So they either lived through the surgery or they died, and either we used the acid or we did not. So if the carbolic acid was used, 34 out of the 40 patients lived through the surgery. If it was not used, 19 out of the 35 patients lived. So we had 75 patients total. 53 lived. So 22 passed away. 16. Okay. So when I'm reading these problems, I like to, this is why I do my notation, because it kind of organizes my thoughts. So the probability that we used the acid and the patient died. So they used the carbolic acid and the patient died, so 6 out of 75 patients. So 0.08. Are the events patient lived and carbolic acid used independent? So again, I'm going to show you both ways. This might be one where you might want to use the second one because we already have part of it done. So this is going to be event E, that the patient lived. This is going to be event F. Again, I can't read your mind, so if you don't want to use words, at least tell me what E and F are. So we're going to look at the probability that the patient lived, given that the acid was used, should equal the probability that they lived in general. So that's one way to do this problem. So given that carbolic acid was used, that they lived. So that was 34 out of 40 patients. How many patients lived total? 53 out of 75. So this is 0.85, 0.707. So again, not equal, so they're not independent. Now, I could use the second one. Again, I might want to because I already have part of it done. So if you see something like this on a quiz or a test, a lot of times I'll give you part of it already to save time. So the probability that acid was used and they died should equal the probability that acid was used times the probability that they died. So acid and died was 0.08. So the probability that acid was used was 40 out of the 75 patients. And then how many died? 22 out of 75. So 0.08, 0.156. Now we didn't use lived because I was like, oh, we can use, but you get the idea. So again, not independent. Okay. So independent rules are, like I said, the biggest thing is to know both of them and to make sure you know how to use that and how to prove things are independent or dependent.